My name's Ron Sluiter. I'm going to be giving a talk on the EPICS motor support. I'm going to start with giving some acknowledgments of the people that have done most of the work that is in the EPICS motor record, because only a small part of it is my doing. Then I'm going to talk about the EPICS motor module itself, the distribution, the tar file, and what's in the tar file, and what is the EPICS support, motor support for. Then I'm going to go into the specifics of what specific device controllers, what manufacturers have support, and I'm going to show where you should look for support and where to ask questions of motor controller support. And then I'm going to get into some of the features of the motor record support. So initially I'm going to talk about the motor module itself and the distribution, and I'm going to narrow down to just the motor record itself, what features it has. Then we're going to go through some configuration example, talk about the specifics of feedback, the retry features, backlash correction, and then finally I'll talk a little bit about the distribution and a little bit of how you configure the motor module for builds. And so this is all the contents here about the latest, using the latest release of the motor record. So let me start with acknowledgments. Jim Kolonkowski was the original author until he left. Tim Mooney and Joe Sullivan took over responsibility until I came and took responsibility for the motor, the EPICS motor, around 98 or 99. And of late, Kevin Peterson and I have been sharing the motor module work. And so again, very little of this work is my work. It's a small collaboration. A lot of the work in there is from Mark Rivers. Everybody in the BCDA, most everybody in the BCDA has done device support for controllers. Diamond Light Source and Mark Rivers 5 or 6 years ago did the ASIN motor. And of late, which is kind of a nice trend, is that we've been getting vendors themselves have been contributing the EPICS support for their controllers, which is most of the work is trying to understand how these controllers work, and obviously the vendors are the best sources to that information. So and it relieves us of the responsibility and the work. So if we're government workers, so we love our abbreviations. So just briefly, when you see MM in this presentation, it refers to the motor module distribution, the tar file, the thing that's distributed on the web page. MR motor record, everybody knows EGUs, units, engineering units, and I usually refer to stepper motors. If I say steps, then I'm talking about a stepper motor, encoder's tick. And I use the words readback and feedback interchangeably. Target position, I refer to the absolute position that the user puts into the MEDM displays, and commanded position as a controller-specific dynamic position that we read from the controller, or the EPICS motor sends to the controller. Okay, so then what is in the motor module? So looking at this from the user's point of view, the most important part is the user displays, the user's interface to the motor record and the device support. And so there is MEDM, CSS-BOY, and CAQTDM supported displays in there. I think a lot of this was Tim Mooney's work in terms of the conversion from MEDM to CSS-BOY and CAQTM. Most of these displays are generic commissioning type displays. There's some of them are application specific, for example, the fly scan. Now, if you see these small print and location since a lot of people, trying to ask where are these files, I've put this in this presentation so that there's some reference to where you will find these things, where you will find these displays. So another thing that's in the motor module is databases, which are primarily substitution or files that are references by substitution files, and then when the startup command runs, it's going to run a db load template, which will load the actual motor records at runtime. There's also some application-specific databases in there also. Some to do with fly scanning again. So then, of course, the motor record itself is in the motor module. It consists of only 2 files, the database definition and about 4,000 lines of source code. And then the other part, needed part, is the device driver support. And basically there's common shared device driver support because the application specific, the controller specific code will not function by itself. Or I should say it would function by itself, but the reason for this is to eliminate duplicated code. Part of the distribution, the common code has 3 different types of the device driver architectures. The original device driver architecture was Model 1, and it's characterized by a unique device support for each one of the controllers. So if you had a new port, the new port 4000 has both device and driver support. Same thing with a Kozu or something like that. For each unique model and unique device support, there's both device and driver code for that. Now, Model 1 uses ASIN for communication, but it's not really a part of the device driver support. It's not included in the code does not reference ASIN. With Model 2 and 3, ASIN became an integral part of the device driver. The Model 2 and 3 use ASIN port drivers. And they have the other characteristics is that they have a common device support for all the device drivers. Another characteristic is that in the Model 1 device drivers architecture, the device support actually did the translation from motor commands into controller-specific commands. In Model 2 and 3, that translation from motor commands to the controller is done at a lower level in the driver itself. Model 2 was an earlier version of what we call ASIN motor. ASIN motor is the architecture that has ASIN as an integral part of the device driver architecture. And it was an earlier version of that. Model 3 of ASIN motor, pretty much I think the thrust was putting more of the work in the common code so that the device-specific code, which is the next slide, becomes even less. There's even less code in it, so that you have a very small file that does the support, and more of the work is done in the common code. Back up here, there is if you want to get into specifics, there is a document Mark Rivers wrote that's distributed with the motor record down there. Okay, then finally, of course, there's device-specific code. There's device-specific directories in the motor module, which contain device driver code and the database definition files for those specific controllers. Another thing that is in there, which you may or may not want to know about or need to know about, Tim Mooney has added some README files to each of these directories identifying which device drivers are which model. That's not complete. There needs to be a little bit more work done on that, but there is some reference there in the README files down in the vendor-specific directories. Another thing that's in the motor module is the save restore files for the record, for the motor record fields. So this is autosave stuff. Now there's a couple items that are build options. One is the IOC build examples that have motor device drivers built in. And the other one is IOC boot examples, which are complements to the build directories. And those can be, by default, aren't built. You can edit the top-level make file and include those examples in those IOC boot directories. Finally, there's a documentation directory that's included that has release notes, the motor record HTML file, some device driver information. The above document from Mark is in there. Okay, and then to some extent, the reason for the motor module is device independence. Basically, it gives you user displays, a user interface, and motor motion behavior that is common for all controllers. So it doesn't matter if you have a servo or a stepper motor or a piezo motor, you will see the same displays and have the same features available to you. And they should behave the same way. So as an example from this display, I could do an absolute move, an incremental move. I could define the current position of the motor, stop the motor from moving, and without having to know what the specific commands are for that motor. The other advantage we get from the motor module is we do have this common code and that gets reused for specific motor controllers, which means it gets ran a lot and debugged a lot. So all three models have common code that is robust. Now the fact that we have a common interface means that there are going to be unsupported motor record features with a specific controller. And that is usually handled by the device driver by typically ignoring that request. So, for example, if you want to set a position in your controller, which I will get into later and what we mean by setting a position, defining a position, if your specific controller doesn't support that, it'll just basically ignore your request and put the position back to where it was. This is basically the price of the design approach to the motor record and motor module, which is a least common denominator approach. We're trying to accommodate those features that are common to all controllers. So this is a list of the 24 different manufacturers that we currently have controller support for. If you want to know the specifics of which models of those manufacturers, there's a number of places you can go, limited number. Probably the best reference would be the motor record itself, the motor record document itself, which I will try to pull up here. So on the header of that motor record document, which you can get off the web or is in the distribution itself, this list here is pretty much the best reference. So it has the name of the manufacturer on the left side, and on the right it'll name, for instance, all these different models. This list was created pretty much as they were added to the motor module. So it's not alphabetical. There's no preferred controllers here. There's just a historical list of as they were added. And it's probably not, I'm not even sure if it's complete, to tell you the truth. Although I think I did determine that there are 24 different manufacturers listed here. But whether or not the specific controllers are all listed, I'm not too sure of. I mean, again, this is because it is a collaboration, and I don't have control or don't want control of every aspect of the motor module. Okay, the other place to look is Epic's hardware support. You can go there and look at the manufacturer and see if they have if there's Epic support. I'm going to pull up the Galil to demonstrate that not everything is in the motor module. I mean, for instance, this top line up here, Mark Clift has Galil support on GitHub. So you may have to look there too. Look outside the motor module distribution. That's not uncommon. Okay, the other place you could look at is Epic's Tech Talk. You could, do a search for there and see what sort of conversations have been going on, if there's been any hits on your particular motor. And finally on this topic is, it is the definition of what consists of a motor is fairly vague. So you can, it does support steppers and servos and piezos, and I mean, you could have an analog output and probably create device support that would satisfy the motor. It really comes down to just satisfying the interface between the motor record and device driver support. I say some comments on the scope of the motor record, because it's as important as what it doesn't do is what it does. And it is limited to single-axis, non-coordinated point-to-point moves. Multi-axis support is distributed with the motor module, but it usually does bypass the motor record itself. So usually any sort of multi-axis or trajectory scanning talks directly to the motor controller, not the motor record. There's a link there to some documentation on multi-axis and trajectory scans. All right, so I'm transitioning here somewhat from talking about the motor module in general to the motor record specifically. So one of the biggest things that the motor record does for you is give you 3 coordinate systems to work with. These 3 coordinate systems are labeled raw, dial, and user. When you enter a position, a absolute position, the motor record does these calculations for you and converts the other 2 coordinate systems for you. So the first thing it does is if you were to enter a raw absolute position, it would use the motor resolution to convert that to update the dial value, and then it would use this direction. These things in boxes are the motor record fields. It would use the direction and an offset to calculate the user. We're going to look at this display quite a bit, so that hopefully by the end, the next half hour, you're comfortable with this display. On this row, is where you'd enter an absolute position. So right now, if I wanted to get a conversion, so say I wanted to set this position to 5 units. I'm going to confuse you by having too many buttons turned on here. So I can set this position in any one of these units on this particular row in an absolute position. Let me get back to this later. Getting back to device support interface, some controllers use raw units to communicate with, which would be low-level steps or encoder ticks. Tends to be more of the older controllers. And then some controllers use engineering units, inches, millimeters, degrees. It's the device support layer's responsibility to handle that conversion between units. These are simply some algebraic expressions of what's shown in that diagram, previous diagram. So I'd like to get to some specifics of how you move a motor and what types of moves. So there's basically 3 different ways of moving the motor in either absolute units, relative units, or incremental. And again, back to this display. So again, this column up here is conveniently labeled move absolute. So if I make a move from here, it's going to move in absolute units. There is a very rarely used field down here called move relative, which allows me to put in a position and move relative. If I keep hitting this enter on that, it'll just keep moving one inch in this case. And then finally, there's the tweak buttons, which have plus, forward, minus, and then of course the tweak value is controlled here. All right, so that shows you where some of these fields are. The absolute being up here, the relative here, and the tweak values. So the other thing when you do move is what are the velocities? How does it control the velocity? So there's a field called the Vmax, which controls the maximum velocity for all the moves. So if you set Vmax, the motor record will go out and check all the other fields that have velocity, and it'll drop that down. Slew velocity is the velocity at which your move should be made at when it's a constant. When it's done doing its acceleration, it should move at the slew velocity. Base velocities for steppers only, used to minimize resonance, which really doesn't show up too much because resonance is really only a problem with full stepping motors. It really shouldn't be much of a problem with micro stepping. And then the other parameter is acceleration time, which does get a little confusing. Let me pop back to that, because I think that's here. So on this row right here gets a little confusing, but it is labeled well. So you'll see here that acceleration is in terms of seconds, which basically both these are in seconds, and it's a way of deriving acceleration by looking at the time from the base velocity up to the slew velocity. So it's a little unusual way of determining acceleration. Jog is different, and it's also well labeled in that it's an actual acceleration rate. No, it's not a time from zero. Again, it depends if you have, if you're dealing with a servo and you have your base velocity set to 0, then yeah, it is the time from 0 to the slew rate. So you're basically setting that time. how long it takes to get from the base velocity to the slew velocity. You're indirectly setting an acceleration rate.
I think he's asking, if you have a base velocity, how long does it take to get from 0 to the base velocity?
Oh, it's instantaneous. So again, if you've got a stepper motor, it's going to start stepping at that base velocity. That's why it's, you know, the more I read about this, it's you know, this again, it was the whole purpose of this was to minimize resonance, and resonance really isn't that much of a problem. And I don't really know. I'm not too sure how much having a base velocity helps, because you could easily, you know, if you don't configure it right, or you could end up hitting your resonance anyway, depending on the load. There's so many factors involved in resonance. And mostly it depends on whether or not it's a micro stepper or not. Full stepping is really the only time you have to worry about this. The assumption is that these basic moves are going to be trapezoidal type moves. They're going to be velocity versus time curves. They're going to linearly accelerate up, move, and then decel down. If you set a base velocity, you just move that graph up to where it just jumps up, linearly accelerates, goes at the slew velocity, decels, and then jumps from there down to 0. That was supposed to keep you from hitting resonance. I don't know how useful that is. Okay? These are where these fields are. These where the velocity and acceleration fields are. Acceleration time is the full time from 0 to the slew velocity. So you're just telling it how fast should it go from 0 to the slew speed. That's where you actually should have your most times. You should probably just set V base to 0, especially if you have a micro stepper. You know, if you're stepping, you know, anything other than full stepping, you probably should just set it to 0. Okay, homing and jogging. There's the fields for homing and jogging. The reason I put these two together is these are basically moves without a destination. A home is not really a move, it's a search. And you don't know where that's going to end up unless you've already tested your system. So these are the type of moves you have to be somewhat careful of. You should at least make sure that you've tested out your limit switches before you do a home search, and also made sure that your home velocity is reasonable and things like that. So these are somewhat types of moves that you have to be a little bit more careful about. So when you're first commissioning a stage, you definitely want to make sure the first thing you should do is check the limit switches, and in general you should make sure that you're aware of pinch hazards, and that EPIX is an open system and anybody can be moving that motor, so you want to make sure that other people are aware that you're going to be near the machine. Servo systems in particular are a little cause for more safety, because they're running off of that feedback loop. Initially, when you're first commissioning them, they may not be tuned well. They can act very violently sometimes. So they need to be, the special concern has to be used with commissioning servo systems. These are where those fields are at, the homing, the jogging. As I mentioned, the jog velocity down here is a little different in that it is in actual units per second squared. Okay, a couple other features: set position and software travel limits. As I mentioned before, most controllers, why didn't it just do that? Most controllers have the capability of having their position defined. So you, as a user, want to move your stage to a certain place and say, I want this position to be a certain number. So that's basically the set operation. there's also, as I may have noticed in the earlier diagram, is that the difference between the user and dial value is there's both a direction, which can change the polarity between the user and dial, and there's also an offset between them. This freeze offset field controls how that works. Let me see if I can. And these things are also somewhat affected. Setting the position and the offsets also affect the travel limits, or the motor record tries to adjust those for you. So I'm going to tell this virtual controller that Kevin Peterson created what its position is. And you'll notice right now I have this field here set to frozen. That tells the motor record not to adjust any of the other coordinate systems. So if I tell this controller I want this to be at 1 inch, both the user and the dial will be 1 inch, and based on the motor resolution, it will set the raw value. Now, if I change this to variable, that is telling the motor record that when I change the user units, or set the user units, I don't want to set the dial and the motor record. I want those to be independent. So now if I set that to 5 inches, you'll notice that this offset was set to 4, and that these values didn't change. Likewise, with this set to variable, I can change the dial units. So now I can redefine this as 10, and that doesn't change the user units, but it does change the offset. So this is the freeze offset, depending on how you want to use it. I get confused with it, so usually I have it set to frozen and want to manually set the offset. But that's how that works. The other thing, as part of the coordinate system, is there's a direction field where you can change the polarity between the dial and the user unit. So if I set this to negative, you'll see that the user units have gone negative. And if I put it back to positive, so this allows you to have polarity between the two. You can also change the motor resolution down here in the lower corner. I don't know if you can see that. I can change the motor resolution to a negative value. I won't get into this, but the software travel limits, again, when you set a position, the motor record tries to adjust those for you so that they are the same relative position. If you want to disable travel limits, you set both the dial high and low values to 0, which will disable them. There's where those fields are at. All right, so this is some other maybe less commonly used features. The motor record does allow you to send command primitives at certain times, pre, post, and initialization time. These command primitives are basically low-level controller commands. You have to know the syntax and the language of the controller in order to put something in there. And of course, that's obviously up to you to put something that the controller will understand. There's also drive power monitoring that doesn't get used too much. There's a status update field right here, which isn't real obvious. This comes in handy, especially with servo systems and feedbacks. This is actually a status update button. Every time I click this status button, it's a request out to the device support to give me, give the motor record updated information. Okay, and there are a few fields that are motor type specific. There are normalized PID parameters. If you have a servo system, you can have the motor record store those values, save and restore those values in the motor record. They're normalized values between 0 and 1 because every controller has a different range. Their PID values will go from 10 to 10,000 or something like that. So in the motor record, they're normalized values. The velocity base obviously is for stepper motors, and there's a done moving input field that's only used for the soft channel device support. Okay, a little bit about position feedback. This can be either done through an EPIX PV link or through the motor controller itself. The motor record can be configured for either one of those. If time permits, I'll try and get into details on that. So this is an example of how to set up your motor resolution field. So the first thing you have to decide if you're commissioning a new stage is you have to decide or ask the user what units he wants the system to be in. Because this field here is right here. I don't know if you can see this up in the corner. I mean, right now it's just a text field. That can be anything. The controller doesn't know that there's inches. It's just used there for documentation, and it's too big to fit. So, so you have to decide which units this is going to be in. This controller is going to be in. And then you have to set the motor resolution to the engineering units per step if you've got a stepper motor, or engineering units per tick if you're dealing with a servo system. So in this example, you have a very simple directly driven stage with a lead screw. Basically, all you have to do is know what the pitch of the lead screw is in engineering units per rev of the lead screw. Multiply that by the number of steps per revolution of the motor, and that's your MRES. If it's a bit more complicated, let me go to the more complicated. There's other ways of setting the MRES. There's other units, which I'm going to skip for now. Actually, I'm going to skip right to this. If you have a gearbox, then it's, obviously you just have to add that gear ratio into this simple algebraic equation. And if it's a servo system, you just change, you just change steps to encoder ticks and run the same numbers. As I mentioned before, there's two different ways of doing feedback, either through the motor, the motor controller itself is providing you with position feedback, or some external device is providing a position feedback to the stage. So, usually this is like a standalone feedback device. So for getting feedback from the driver support, the device driver has to support this. So it has to communicate this to the motor record, which it does by setting a status bit in a field called the MSTA, and basically it just says that encoder is present. And if that's the case, then the raw encoder position field will show you those raw values. Let's see. So if that's the case, then you need to know what the resolution is of that encoder device and set the ERES field. And then you have to tell it to use that encoder device in the calculations by setting UEIP to yes. I don't have a slide showing these things. Unfortunately, I can show you where they are here. So if you can see this cursor, this is the encoder resolution field, and for some reason I have UEIP set to yes, which I'm sure the underlying controller doesn't support that in this case. Another hidden and fairly useful display created by John Hammonds, down in this lower right-hand corner, there's a field called the MSTA, and he has this nice pop-up that shows you the details of that. So this is usually only used for diagnostic purposes. There's limit switch status here, so you could conceivably pull this up. If you have limit switches, you can toggle. And you could monitor them from here. This display is really for commissioning and configuring. Your user shouldn't be seeing anything other than these displays. This is one that Pete created many years ago. It only is accessible in this pop-up display because unfortunately we didn't add it to the other displays, but it's rather convenient because it allows you to do two things fairly quickly, and one is to be able to change the tweak value. It does require that you have, in order to change it, you have to have software travel limits configured. But you'll see right now I've got the tweak is set to 1 inch, and I can conveniently change these by factor of 10 back and forth like this. I probably hit the limit. So, and you can also change the speed. So right now the speed is set to 1 inch per second, but I can change that by a factor of 10 very conveniently this way. So that's a fairly handy screen. Oh, this is, okay, basically if you're configuring feedback from an Epix PV, then you're using the readback link field, the raw res, and URIP. Let me point those out so you know what those are. Basically, this is the readback link is down here. To tell the controller to use that field in the readback calculation, you have to set URIP to yes, and then of course you have to tell it what the resolution is of the feedback. If you have a standalone device that's giving you engineering units, then you would just set the raw res to 1, and that's very common. But if it's telling you steps or encoder ticks or something else, then you have to set the raw res to something to match these engineering units. This is probably the diagram I refer back to when I'm trying to remember how the motor record works. And basically it's a data flow diagram that has two logic blocks here, one to do with the controller's feedback, and the other one has to do with the feedback coming back from an Epix PV link. And this one here controls these two switches, and this logic block controls this switch here. So basically, where you get your readback from, which is, let me pop back to this display again. All right, so this is your user readback value here. And basically this diagram tells you where you're getting that from. So that user readback value and the dial readback value can either come from the commanded position of the motor controller, which means there is no feedback. You're just being shown what the current commanded position of the device is. Or it can come back from the raw encoder position, so it is showing you the feedback. Or this logic is false, this is true, and you're getting your readback from an external standalone device. And so basically you have, that's the case, then you're getting numbers from this readback link, you're multiplying that times the raw resolution and then feeding that into the dial. So this is where a lot of these fields that I just mentioned are at, and I'll move on from there. All right, so let me talk a little bit about retries. And first let me say what it isn't. It's not a continuous closed loop dynamic loop closure. This is retries via the motor record. There are supposedly controllers out there. I have not had any experience with them that can actually do I guess I'm referring to stepper motors that will actually adjust the position based on feedback on the fly. But I haven't worked with any of those. This is the motor record retries where when you're done with the move, it calculates the air and then does a move after that. So it tries to eliminate the dial position error, which I think is defined down here. That's the dial position error. It's the dial value minus the dial readback value. And so at the end of the move, it'll do that calculation, see that error, and then if this logic is true, and I don't want to get into the logic, then it'll do a relative move somewhat in the background. So it's basically doing relative moves down to the controller or device support. It's telling device support, do this relative move, but it's not changing your target position. Your absolute positions are the same. So this is done kind of backdoor relative moves. And it'll keep doing that for as long as the retry count isn't exhausted. So in order to configure retries, well, actually, this is when you don't configure. If you have a servo motor, you really shouldn't be doing retries. Obviously, the controller itself is doing the closed loop, and you don't need retries. This is really only for stepper motors or maybe piezos. So the things you have to configure for this is a retry deadband and the maximum number of counts, maximum number of retries that you want the system to do. There is also a retry mode, but I won't get into that. I mean, the mode right now is basically if for instance, if the motor stops moving and you have, retries set to 5, it'll just, and your air is 1 inch, it'll just 5 times tell the thing to move 1 inch to try and eliminate the dial readback error. No, it just basically, it's, some reasonable non-zero value. I mean, if you get it up too high, then you're just wasting time. And a lot of times, if you're doing step scans, the user doesn't want to sit there at that position, for that amount of time. So, 5, 10 is probably the most you'd want to set it to. There's where those fields are at. I'm going to talk briefly about backlash correction. So if these gears that you see up there at the top of the page are not perfectly meshed, then you get backlash. That's the definition, or that's an example of backlash. It's lost mechanical motion. And you configure that with, you configure the motor record to do backlash correction using the backlash distance field, which determines the magnitude and the direction of the backlash move. And backlash has its own velocity and acceleration parameter. And the reason why it has its own velocity and acceleration is obviously you're making your slew move is going to be very fast, and you want the backlash correction to be very low velocity and lower acceleration than your slew, because you want these things to engage and stay engaged as they're making their backlash move. So you don't want to go real fast or accelerate real quickly to have them disengage again. So the force is engaged in one direction. So the terminology is that they call the backlash, the sign of the backlash distance is the preferred direction. And let's see, I've got some logic here that I don't want to get into, or don't have time to get in, really don't want to get into. This is where these values are at. That's where you define the velocity, the acceleration, and the distance. So basically, if the distance is positive, no matter what you do to that stage, that last move is going to be that direction. If it's positive, the last move is always going to be positive. If you set the backlash distance to negative, the last move is always going to be negative. There'll be a small negative move to keep the the backlash force engaged in that direction. I'm wrapping up. And so this is where the motor record web page is at. There's where all the versions are at. And I should have mentioned this right from the beginning, but I didn't, is that the motor module is part of the Synapse distribution. And this is a subpage of the Synapse web page, which you can get from the Epic's homepage too. So basically in that list of all those modules included, the motor module is one of them. Let's see. All right, a little bit about customization. Some people, it's the easiest thing to do is just use the motor module and Synapse for that matter as is. If people want to tailor it, first of all, the first customization, as I mentioned before, is there's examples there. If you on-comment, there are 3 lines in the top-level make you can build the motor IOC boot and motor example applications and look at those, use those examples. In terms of the motor configure release file, it only needs Epic's base, but if you don't define any of the links to other modules, the only thing you'll get is the OMS device drivers and soft channel device support. So you really won't get much if you don't define other modules, specifically ASIN. If you don't define ASIN, you're not going to get a whole lot. And there's also, if you want to tailor the build on a vendor base on manufacturers, then there's the motor app make file. You can comment out those modules from there and only build the device support that you want. And then that's it. I'm done. Thank you.